Okay, 8.5, solving exponential equations. So two exponential expressions with the same base are equal when their exponents are equal. Okay, so for example, if a to the m equals a to the n, see this m and n? That means we can drop the a's and m equals n. Okay, and obviously the base has to be greater than 0. We can't have 0 to some exponent, right? That doesn't make sense. And we can't have 1 to some exponent. And we know that because that would just be the horizontal line at 1. Okay, so we can't have that either. Okay, and then m and n are like real numbers. So here are some more formulas and some more laws. Log of 1. So log base b1 equals 0. That's because any number to the exponent 0 is going to give you 1. Remember, what base, like this base to what exponent is going to give you 1? That's what it's asking. Okay? And we have the general log of b to the x. So log base b to the b to the x, again, remember that cancels out, and we have x equals x. Okay, and I'm going to show you the change of base formula. So if you want to calculate this in your calculator, remember, your calculator, that log is actually log base 10. This is the calculator one. So if you have log of any other number, what you'd have to do in your calculator would you'd have to put log x divided by log a. And then you can assess both of those with that base 10 in your calculator. And you can, basically what that's doing is changing the base to base 10. Okay, now log of a number equals log of a number. So log x equals log y. As long as we have one log on each side, we can cancel those out and we can have x equals y. They must have the same base. Must have same base. This example here has a base of 10 on each, but it just has to have the same base in general. Okay? And we saw this in the last lesson. B to the log base b x equals x. Of course, this cancels out, x equals x. And rewriting this, but instead of the b, if we had like the base 10, n to the log base 10 x equals x, this can cancel out, and we're going to have x equals x. Okay, so just a few more logarithm laws that we're going to be working with. Okay, so example 1, use the laws of logarithms to solve for x. Okay, so we have a variety of approaches in this lesson. For 2 to the x equals 32. So for the scope of this, I'm going to do what's straightforward. So I'm going to say that this can say 2 to the x equals 2 to what exponent? 5. And I get x equals 5. Okay? For b, same idea. 3 to the x equals, well, we have 1 over 27. So 3 cubed is 27. So 3 to the negative 3 is going to be 1 over 27. Okay, so x equals negative 3. Okay, now c. We have 2 to the x equals 12. Here's the issue. We can't change 12 to have to be a base of 2. So what I'm going to do is I'm going to log both sides. And I'm going to get log 2 to the x equals log of 12. I'm going to bring this x in front. And I'm going to have x log 2 equals log 12. One thing that we have to remember right here is that log 2 and log 12 are just numbers. So I'm going to go ahead and divide both sides by log of 2. those are going to cancel. The exact value is going to be log of 12 divided by log of 2. And you can leave it like this, because in your calculator, if you put this in, it's going to be not exact. It's going to be a big decimal. Okay, D, x equals log base 6 of 216. So 216 can be rewritten. So I get log base 6, and that's 6 cubed. Okay, so the log base 6 cancels out, and we get x equals 3. Okay, looking at E, 49 to the 2x minus 1 equals root 7. So I can rewrite 49 as a base of 7. How I would rewrite this number right here is 7 squared, right? And then I'm going to have 2x minus 1 in the exponent. And how I would rewrite root 7 is 7 to the 1/2. Now, remember, exponent to an exponent is multiplication. So if we were to multiply this, we would have to distribute the 2 into the 2x minus 1. So that's going to actually be 4x minus 2. Okay, and the other side of the equation stays as 7 to the 1/2. At this point, we can drop both bases, and we get 4x minus 2 equals 1/2. You know what, I'm going to write this as a fraction. Okay, I'm going to bring the negative 2 over, and we're going to get plus 2. Right, so I get 4x equals 1/2 plus 2 is 2 is actually 4 over 2. So that's 5/2. Okay, and then that 4 comes down. We get x equals 5 over 8. Okay, the other way you can do that, instead of like a cross multiplication, you can divide both sides by 4. So that would be like 2 times 4 in the denominator. So f is a little bit different, okay? We have to think back to exponential functions. We have 5 times 2 to the 2x minus 1 equals 640. Okay, this is a warning. We have to use BEDMAS. So when we're taking a look at BEDMAS, we cannot multiply these bases because 5 is not part of the base. Okay, we would have to apply the exponent laws before multiplication. So instead, I'm going to get that 5 out of there. I'm going to divide both sides by 5. So we're going to do 640 divided by 5. I get 128. Okay, so I'm going to rewrite 2 to the 2x minus 1. And we can rewrite 128 as 2 to the 7. Okay, because we have the same bases, we can drop the bases, and we get 2x minus 1 equals 7. We want to bring over the negative 1. It becomes positive 1. We get 2x equals 8. Divide by 2. Our answer is x equals 4. Okay, so we're going to build on our skills. So now we have 3 to the x minus 12 equals 69. So let's bring over the negative 12, and we're going to get 3x equals 69 plus 12. Okay, which is 81. Now we know that 3 cubed is 81. No, 3 to the exponent 4. All right, so 3 to the x is going to equal, we're going to sub in 3 to the 4, exactly where this 81 is. Those two are equivalent, so we can do that. And we get x equals 4. Okay, now h, we get 10 to the x plus 1 equals 721. Okay, obviously this doesn't look like a base of 10. Base of 10 would be like 10, 100, 1,000, and so on. So what we're going to do, and this is the first time we're seeing this, is we're going to log both sides. So how that's going to look is log, and our natural log is like, I shouldn't call it natural log, that's something different. So this is the general log that we use in our calculator is log base 10. Okay, and especially because this base is 10, we want to apply log base 10 to both sides. I think that that's a better explanation. Okay, so in our calculators, log base 10 of 10, that cancels out. We get x plus 1 equals log base 10 of 721. Now, we need to know what number this actually is, and we're going to get it probably an ugly fraction. So we can do log 721 over log of 10, and that's that change of base formula. Okay, if you want to check it, we get an ugly decimal, so we can just leave it like that and bring over the 1. I get x equals log of 721 over log of 10 minus 1. We can either write it like this, or we could have kept log base 10 of 721, because that's a number, and then minus 1. Either of these two ways you can express. Okay, using common factoring. So here is a new method that we can use with exponents and logarithms. Okay, so sometimes the terms on one side of the equation cannot be combined. So an example of this is for a, 2 to the x plus 2 plus 2 to the x. Those cannot be combined. You can't just add, like we can't apply exponent laws with addition or subtraction. We apply exponent laws with with multiplication or division, right? Or power to a power. So we can't collect those. So instead, what we can do is we can see that both of these have a base of 2. So we can go ahead and common factor out a 2 to the x before we rearrange. And what that's going to do is, for example, if we factor out a 2 to the x out of these two terms, we know that we have to put the common factor first. So this is common factor. And we're going to have some bracket for what's left over. Okay. And we didn't move over the 320. So we don't have to divide, common factor out the 2 to the x out of the 320, just out of the first two terms. So I want to point this out, because now we're going from something that is usually our solution to, for example, if we had a to the x times a to the 1, what we usually do is combine these exponents and we would have a to the x plus 1. What we're looking at it is now is a little bit backward. We're dividing out that 2 to the x. So 2 to the x is gone. And now we have 2 squared. So this is going to be 2 squared. And those are multiplied by one another. 2 to the x plus 2 could be written as 2 to the x times 2 to the 2. Right? And then plus 2 to the x divided by 2 to the x is just 1. Okay, so now we have 2 to the x bracket. We're going to have 4 plus 1 equals 320, which is just 5, right? So at this point, it becomes one of our questions from example 1, where we can't multiply these two terms because exponents gets applied in BEDMAS before multiplication. So we can go ahead and divide out the 5, and we get 2 to the x equals 320 divided by 5 is 64. Okay, 64 is another way of saying 2 to the 6. So our answer is x equals 6. All right, let's do the exact same thing for b. We have 10 to the x plus 1 minus 10 to the x, we know that we're not applying an exponent law here, okay? Even though we have two bases that are the same, exponent laws do not apply for subtraction. Okay, equals 9,000. So let's divide both of these by 10 to the x. The common factor goes in front, and then we're going to have some bracket equals 9,000. So we have 10 to the 1 minus 1. Okay, so we have 10 to the x, bracketed, 10 minus 1 is 9, equals 9,000. Same thing, we cannot multiply 10 to the x and 9. Do not multiply those bases. We have to consider bed mass. So instead, divide out the 9. And we're left with 10 to the x equals 1,000. Okay, we get 10 to the x equals 10 to the 3, x equals 3. Okay, scroll over. So now we have C, 2 to the 2x minus 3 to the 2x, or 2 to the x equals 4. What we're going to do is we're going to use the substitution method this time. Because we have this 2x, we can't just divide out 2 to the x. Okay, so the substitution method, what we're going to sub in for is m is going to now equal 2 to the x. So this is 2 to the 2x. This 2 to the x is going to equal m, and then we're still going to have this squared. Okay, minus 3, 2 to the x is going to be m. And I'm going to bring this 4 over. We have negative 4 equals 0. Okay, now we're going to factor. What two numbers multiply to negative 4 add to negative 3? I get negative 4 and 1. So I get m minus 4, m plus 1 equals 0. Let's branch these off and solve. I get m equals 4 and m equals negative 1. But because we subbed in, we now have to sub back in for the m. So I get 2 to the x equals 4 as one of my solutions, and 2 to the x equals negative 1. Well, 2 to the x is never going to equal a negative number. Okay, this is inadmissible. Okay, if you think about the graph 2 to the x, it's right here. The range is from 0 to infinity. So it's never going to equal negative 1, no matter what x value you put in for it. And then this side, 2 to the x equals 4. I'm just going to do 2 to the x equals 2 to the 2, x equals 2. So that is our solution. Right. Both sides of the equation cannot be written with the same base. This is what we do. If two expressions are equal, taking equal, as in there's an equal sign in it, taking the log of both expressions maintains their equality, right? It's kind of like what you do to the left-hand side, you do to the right-hand side. So, for example, if m equals n, then log base am equals log base an. Okay, and of course, the base can't be 0 or 1, even less than 1. Even less than 1. Okay, and m and n have to be greater than 0 as well. Okay, because you can't log a negative number. So steps. Take the log of both sides of the equation, and then we can just use the base of 10. Okay, use the power rule for logarithms to rewrite both sides of the equation with no exponents. You know what? Let's do those for example 3a. Okay, so, and then we'll keep going with the steps. So example 3, solve. We have 2 to the x plus 1 and 3 to the x minus 1. Since these are different bases and we cannot rewrite the 2 as a 3 or a 3 as a 2, not without doing a decimal and trial and error, right? We want exact answers. I'm going to log the left-hand side, giving us log, and then, of course, base 10, 2 to the x plus 1. And I'm going to log the right-hand side. So log 3x minus 1. And then what I'm going to do is I'm going to take this power rule and move the x plus 1 in front of the log 2. And I'm going to move this x minus 1 in front of the log 3. What this is going to give us is x plus 1 log 2. And I'm going to get x minus 1 log 3. I'm not going to write the base of 10 because it is a given that if we don't write the base, that it's by default the base of 10. Okay, now the next step is expand using distributive property. Let's go ahead and apply this log 2 onto the x. We're going to get x log 2 plus log 2 times 1 is just log 2. Okay, expand the right-hand side. We're going to expand this log 3 onto the x. We get x log 3 minus log 3. And remember, log 3, just on the side of the paper, is just a number. It's approximately like 0.47712 and so on. Log 2 is also a number, right? So we're just expanding this number. It's like 0.30102 and so on. Okay, and then the last step, collect like terms, common factor, and divide out and solve. Okay, so the like terms are going to be the x terms. I'm going to bring this x over here. I have x log 2 minus x log 3. Log 2 and log 3 are not like, those are those decimals that I put in the top right corner. They are not like terms. You can't just subtract the 2 and the 3. Okay, don't do that. Okay, and on this side, I'm going to take this log 2 and move it over. So we're going to have negative log 3 minus log 2. Okay, how I isolate for x is by common factoring the x out of the first two terms. So I'm going to have x log 2 minus log 3. Log 2 minus log 3 is just a number. Okay, and it's going to equal negative log 3 minus log 2. Okay, since this is just a number, there's no variable in here, I'm going to divide both sides by log 2 minus log 3. Okay, and my final answer for exact value, I get x equals negative log 3 minus log 2 over log 2 minus log 3. Okay, so b 3 to the 2x plus 1 equals 4 to the x. Okay, the bases 3 and 4, we can't write those as the same. So let's go ahead and log both sides. We're going to get log 3 to the 2x plus 1 equals log 4 to the x. Okay, let's use the power rule to bring down this 2x plus 1, bring down this x. Now we're going to have it look like 2x plus 1 log 3 equals x log 4. Okay, let's go ahead and distribute the log 3 into the bracket. We get 2x log 3. Do not multiply the 2 and the 3. Okay, this log is basically an operation. The log 3 has to stick together. Like log 3 is a single number. Okay, and then we have plus log 3 equals x log 4. Okay, let's go ahead and bring this, you know what, let's bring this over here and then this over here. Okay, so we're going to get 2x log 3 minus x log 4 equals negative log 3. Okay, in order to, like, we can't collect these because they're not like, they both have an x, So it's kind of like we're collecting them, but what I'm going to do formally is I'm going to factor out the x. Okay, so we have 2 log 3 minus log 4. Okay, and that equals negative log 3. And because 2 log 3 minus log 4 is just a number, we can divide both sides by 2 log 3 minus log 4. Okay, so in total, we get x equals negative log 3 over 2 log 3 minus log 4. And that is our answer in exact value. Okay, a person wants to invest $5,000 in a tax-free savings account, and it grows at a rate of 9% compounded annually. So 9% is going to be the interest rate, and that's 0.09. We always want to convert a percentage. Because there's like a unit on that, we want to convert it into a decimal so that we can use it in this equation. Okay, the principal is how much you put in, so that's $5,000. Okay, and this question is how long will it take the investment to be worth $7,000? So the amount that it's going to pump out is $7,000. We don't know the how long, right? The time. So as a review, actually, I'll just put them beside. Okay. So N is time in compounding periods. We don't have to worry about the compounding periods in this case because in this scenario, it's just annually. So it only compounds once a year. Okay. So in this case, it's years. Years in this question. Okay. Amount is the amount that we have after. Amount we have at the end. Okay. Principal is amount, initial amount. So amount we start with. And 0.09 is the interest rate as a decimal. Okay, so if we have A equals P, 1 plus I to the N, we can sub all these values in and we get 7,000 equals 5,000, 1.09 to the exponent N. Okay, that's just taking those numbers and subbing them directly in. All right, so as a reminder, 5,000 and 1.09 cannot be multiplied because we'd have to do BEDMAS, we have to do the exponent first. So instead, we can divide out both sides by 5,000. Okay, so 7,000 divided by 5,000 is 1.4 equals 1.09 to the N. Okay, so in grade 11, what we would do is we would plug in different numbers for 1.09 to different exponents, and we try to match the 1.4, and it would be approximate. Now that we're in grade 12, what we're going to do is we're going to log both sides. Okay, so now what we have is we have log of 1.4 equals log of 1.09 to the N. But we can take that N and we can bring it down. So we have log of 1.4 equals N, log of 1.09. Okay, so in order to isolate the N, we're going to divide both sides by log 1.09. Okay, so N equals log of 1.4 divided by log of 1.09. Okay, that's an exact value. If we want to actually know what that means, let's go ahead and just divide that in our calculators because both of these are base 10 and we get 3.9. And in the context of this question, the 3.9 is appropriate. Okay, so how long will it take the investment to be worth $7,000? So I'll put it up here. Therefore, the investment will be worth $7,000 in 3.9 years.